All right, so again, talking here about position, velocity, and acceleration, their relations with derivative. Another situation that practically comes up quite frequently, relates to physics as well, is projectile motion. So here, you want to think of like the classic example, like the baseball player hitting the ball and the ball sort of flying through the air on its way to ultimately wherever it lands. And when we're in this situation, the sort of most interesting formula that relates to this is often the height of the object. So this function s of t here, in the case of a projectile motion, is going to be describing how far the object is off the ground. So initially the object would have been whatever height it was off the ground, I suppose, but then eventually the ball is going to get down to where it would hit the earth, reaching some apex point along the way. So one question that you could ask is, when does the ball reach its highest point? Well, on some level, the ball reaches its highest point when the height function gives you the largest value that it does. I mean, if the height function is providing you with information about height, then if you just knew when the height function was at a maximum, you would know when the ball reached its highest point. But now here's the challenge there. Who knows how long this ball was in the air? Maybe it was in the air for 4 seconds. So what are you going to do? Are you going to throw in and test at 0 seconds, at 1 second, at 2 seconds, at 3 seconds, at 4 seconds, and just take the highest measure? Because if all you looked at was at 1 second, 2 seconds, 3 seconds, and 4 seconds, maybe 2 seconds came out to be the highest. But just because 2 seconds was the highest, is that guaranteed that that's the time of the highest height? Because maybe the highest height wasn't at 2 seconds, but at 2.2 seconds. So you got to think for a second, you got to be like, man, how are we going to get a grip on when the ball reaches its highest point? And the answer to that is not to think in terms of the height of the object, but to use derivative and get yourself a function of the velocity of the object. Now, to be clear, we're not talking about any kind of velocity. We're talking about the velocity with respect to height. So since we're measuring height, which is a vertical position, we're going to be measuring velocity in the vertical sense as well. So, if you think of velocity vertically as opposed to horizontally, whereas horizontally right was positive and left was negative, vertically up is positive and down is negative. So if we think of the velocity of the object here, the velocity being positive means the motion is up. So when the ball is struck, the velocity is positive as the ball ascends. On the flip side, velocity is negative when the motion is down. So after the ball reaches its apex, the velocity is negative because the ball is falling. But now, think about that for a second. Because if the velocity is positive when the ball is ascending, and the velocity is negative when the ball is descending, when does the ball reach its highest point? Well, the ball goes up and then comes down. And actually at the point where the ball makes a shift from going up to going down is precisely where the ball is at its highest point. When the ball shifts from positive velocity to negative velocity, you're at your highest point. And then you ask yourself, where do you shift from the positives to the negatives? Well, it's 0. So when does the ball reach its highest point? When the velocity is 0. And if you think about that even deeper, that actually kind of makes sense. Because if you throw something up and it comes down for a split instant, second, not even a second, it's just a fraction of a second, at the top of its motion, the ball has a velocity of 0. It's practically frozen in time for that brief second before it changes direction and starts to proceed in motion downwards. So when does the ball reach its highest point? Well, when the velocity is 0. Now, here's another question you could ask that relates to this situation, which would be another relevant question in light of, like, say you've got the classic example of the baseball player hitting the ball and striking it into the air. The ball's got to land eventually. One question you could ask is, when does the ball land? When does the ball land? Well, how can we address this? What is going on when the ball strikes the earth? Does that have anything to do with velocity? Well, if we knew when the ball landed, we could plug that time into the velocity function to see what the velocity was at that moment. We know that the velocity would be negative because the ball is going downward at that point. But that doesn't tell us exactly when, because we have to know when the ball would land in order to get the information about velocity. But what do we know at the moment the ball lands? We know that the height of the object is not above the earth, not below the earth, but at earth level. And we have something that can tell us what the height of the object is. So when the ball is hit, the height is going up and is positively changing. When the ball starts falling down, the height is still positive, but now is changing negatively because the height is falling. But when the ball hits the ground is precisely when we are at a height of 0. That's precisely when our position function is 0. So when does the ball land? The ball lands when the position function is at 0, when the height is at 0. Because you've got to agree with me, right? The height going up positive, going down, ultimately to 0 whenever you are at that height. Every time you are every second you are above the earth, your height is positive, and if you could be below the earth, of course that wouldn't be possible in a physical sense, but if you could be below the earth, your height would be negative below the earth. But the line at which the earth is when your height is 0.